I have a stupid notation question. Why does cap x only have 3 lines across on the 4 sides?
Because that one is there, and you just can't see it. So, I don't know.
You never ran.
Sometimes it's
human stuff. Yeah. What's that?
It's a rare occasion for the fourth one.
That's
I'm also
interesting.
trying to be figuring out like when you put capital letters versus lowercase letters.
Yeah, the I's are oftentimes lowercase, but it's not super consistent. I don't know. I think it's just human stuff. I got a couple ways of doing things, and I play jazz, so they met it. Funny ways. You probably do the same thing.
Now I copy some.
Oh, you have.
Like my cap x's and I'm just reading them.
So you don't have a reason for that. You can say,
Yeah.
stop. You did that. Let's get started. Welcome back, everybody. We're going to come back to that simulation study and kind of spend some time playing around with the controls of that simulation. We just saw a quick preview of it last time. I do want to write down forms of the likelihood function when we're just considering mu in the normal example, so you can see all the different ways I can jump around on that equation and why you might handle that equation differently at different times, especially on like a midterm or a final where you're trying to state time. But we'll try to distinguish when it matters, and I'll teach you a lesson early in this class, and I'll remind you about this lesson when we get there. So it's kind of one of the common mistakes that I've seen in my Bayes class over the 18 years that I've taught this. Let's just try to answer this question. So this word right here, Bayesian, I say it like that. So why? I don't know. That's the way I like to say it. That's the way I pronounce things. There's other ways to say it. So other ways that people say it. Have you heard any other pronunciation? Bayesian. And I find that one useful if you're going to incorporate it into a song and you needed 2 syllables. So you can use the Bayesian thing. So you hear that like in India all the time. So all the Indians say Bayesian. And then you hear the hybrid, Bayesian. So, and who knows? Why do you pick one over the other? So Bayesian, why do I like what I like? Because I don't know about anybody that says Bayes' rule. So, so inconsistencies all over the place. How would Bayes have said this? He didn't say it. So that's what this paper is about. So he never invoked the rule. Bayes wrote a probability rule. And we know what that rule looks like, and it's for switching the conditional orders in a distribution. We've looked at that rule quite a few times. The way Bayesians use that rule, or Bayesians, all the same thing, that's what makes you a Bayesian. So not that you adhere to the probability rule, is that we use it on updating things that are unknown in our probability distribution. So we might have the same models as everybody else, or the same likelihood functions, and how we treat the parameters and learn those parameters is different. Sometimes we get the same solutions, but how Bayesian operates is through Bayes' rule, where they take the likelihood and they update all the unknowns, maybe the parameters of that function, up to random variables. And then they do inference off of those unknowns, and they put probability measures on that. That's what all Bayesians have in common. How they do that might be different. How they construct likelihoods, they might be semi-parametric people. They don't like parametric models, and that's what we've been handling in this class. They might have different approaches to how they come up with a problem. And then there's a lot of commonalities that all Bayesians do. And they might explain it differently to you. And that's kind of the philosophical, runaway, is how you think about it all. And so far I've taken a very engineering approach, and I just said, let's do some stuff. So I think starting next time we'll get into a little bit more of the philosophies and the whys, and can I say more about it? I think we can say lots and lots about things. So we're going to try to balance, kind of engineer what do you all do, what does everybody do, they all do the exact same thing. I think for learning mu in a normal distribution, we all think x bar is a pretty good estimator. If we we think the data was actually normally distributed. Sometimes we don't think the data is normally distributed and we use X bar and things go awry. And so the problem is obvious. So it's that we're mistreating things and not modeling things appropriately. But if you thought everything was normally distributed, you'd need a lot of information about what the mean was before you were willing to say some answer that's different from X bar. And so we all kind of agree whether or not we're classicists or frequentists or Bayesians or however we say things. So we all kind of agree that's a good answer. So we're going to think about that answer a couple different ways starting next time. Today we're just going to write down a prior and talk about this answer right here that we looked at. Next time we'll take the engineering approach, just here's what most people do. And next time we'll start on whys. I think we'll spend a little bit of time on simulation, and what I want you to glean out of this is just what a beta distribution looks like, basically, and how flexible it is, and that the Bayesian answer is working. So again, a little bit more on engineering. Who coined the term? So this was one of your homework problems. I read through the solutions real quickly. Jay Young hasn't graded it because there's been a few stragglers, and I said, okay, we'll get to it on Monday. So if you haven't turned it in yet, we're going to start grading it today, and that's where the penalty really comes down. So the reality of the class is if Jay Young starts grading something and you're still late, if it causes him trouble, we'll let you know. So we'll take off a few extra points. But if you do turn it in to me before today, I think you're within the grace period. So we have a practical grace period. And it's rate limit, it's stochastic too. So be careful with that, bless you. I did read the most common answer, and most people said Fisher. And it's one of the very earliest comments in the paper that Fisher wrote down this in one of his expositions. So he stated the term Fisher, somebody's come up with that, found it in some previously written stuff, and this happened a long time before the word got popularized. I don't know if people noticed. I don't think that people were running around saying the term loosely and just not writing it down. I've had the good fortune of knowing people that overlap the time period. So most of them have passed away, including who I usually attribute the answer to, and including all the people that we would attribute the answer to. But a couple of these people I got the great pleasure of sitting down and talking to, including Steve Feinberg, who wrote the paper. So we had a beer early in my career, and he told me one of the greatest parts of being a statistician is being able to meet young researchers and have a beer and talk about things just like this question. So lucky me. I don't know if I'd be so generous, when I was off at conferences, but he was super generous with his time, and that's what made him popular. It made him ask questions like this. So he writes a very long-winded answer to this question. I don't think he exactly answers it. So who coined the term? So when did Bayesian become Bayesian? And that's my interpretation. So you might ask me, what do I mean when I say who coined it? I'm kind of saying, like, who popularized it. But nobody asked me what exactly I meant by coining a term. So this is not a wrong answer. You could argue that. A historian could argue that. So I think other arguments could be made as well. Any other good answers? What does the paper actually say? It doesn't say this. So this isn't a literature class, so I'm not going to grade you on, read this thoroughly and understand the essence. I get it too. I read Shakespeare. I don't know what the essence is.
I thought it was Savage.
Savage?
Savage, yeah, because I think he really started using it. Not only just mentioned it.
Yeah, so maybe Savage. I think this is a really good answer. So I think Savage probably is the one that popularized a lot of the terms. So he wrote Foundations of Statistics, it's a cool book, it's still provocative. I still have it on my shelf of favorite books. So once upon a time, I used to like to read through stuff like that. Have you read Foundations of Statistics? No. Anybody read Foundations of Statistics yet? Alan? No, not yet. Okay, so maybe after, I didn't read it until I was in my last year of graduate school. So I wanted to make sure I had my ducks in a row and I could talk to people about the foundations. Savage is probably our first mega Bayesian out there that just starts using it all the time in applications and in theory. And he's carving out both paths, and he has a swath of graduate students. Bless you. So I think that's what makes him popular. You have all these grad students, dozens of them, and he creates this lineage. And so, and it becomes super popular. He was at the University of Chicago doing all of this, so he's in a powerhouse place as well. So it gets a lot of exposure for a lot of different reasons. But somebody told him the term. So somebody came over, saw Savage, and said, hey, what do you think about the term Bayesian? So if I tell you that that happened, did Savage really coin it? I think he can still be credited for popularizing it. But somebody told it to him. And it says it in the paper, and it's very brief. It's Jack Good. So I.J. Good. So I.J., i.e. Jack, Good. So I.J. Does anybody know what I is? Irving. That's not quite right. It's actually Isidore. So it's interesting how names change over time. And so Jack wanted to just be Jack. You know, so if you want to change your name, there's no better reason, in fact, good reason to do it than just you feel like it. So he's Jack Good. So just kind of out of nowhere. This is John. So it's interesting. So he just decides to be Jack. So Jack Good reads it somewhere. He reads it as he's reviewing a paper from Dave Finetti. So Dave Finetti, we'll talk a little bit about him, and if I were in a hardcore Bayes class, I'd probably be kicking off with Dave Finetti's theorem and telling you what he told us about things. And I'll allude to it in this class. It's not exactly what I want to build this whole class about. We'll be subscribing to Dave Finetti's theorem regularly throughout this class, consistently all the time. And later on, I'll tell you what it says. He ended up writing the term in a paper based on N. So he substituted that A for an E. And he wrote it a little bit different, and it was only in the title of his paper. And Jack happened to be looking at this paper.
Are there any test questions on
No, nothing like that. Nothing like that. I found it interesting. I got to talk to Jack about it for many, many hours, and I got to talk to Steve about it for many, many hours, and I really enjoyed it. I thought it was cool. What happened? Who are these people? I think a lot can be addressed by when did people come up with things, and what were they doing, and what were they thinking about, and does that apply today? And sometimes when we don't think about it and we say, well, people do this, they misunderstand the context of things. So I still like history. I'm getting a little bit old, but I liked it when I was your age too. So we can enjoy it, but I won't test you on it. So he replaces E for A, and Jack reads it, and he thinks, that's cool. And Jack's a little difficult to follow sometimes because he incorporates humor into his writing. So he has puns, and you can't tell when he's serious unless you know the guy. But he likes wordsmithing things. He tells the term to Savage. Jack writes over 2,000 articles in his time. He has 3 graduate students. During the whole period, none of them become faculty member. David was not a student. So if those of you know who I'm talking about. So his actual PhD students, nobody carries the torch. And his papers are really difficult to read. So he likes them to be thoroughly cited, correctly cited, thousands of citations, and he's terse, and you need to know what all the citations mean to follow his papers. And Savage had students and grad students writing papers, so he's constantly having to explain things to people and making sure it's readable, because he doesn't have time to explain it to people all the time. So they're really clear about things. I think the answer is actually Dave Finetti tells Jack, tells Savage, and Savage makes it explode. So just like all questions that are historically based, there's multiple answers. This is not incorrect. So, and probably your next question is, if we didn't answer correctly, how much did we miss on the homework? Like a point. It will have no relevance in the rest of your life other than this story. So, no big deal. This is just to make sure you want to read some papers and stuff like that. Founder of Bayesian Statistics. That's contentious as well. So all fields or built by lots of people. I like to say Laplace. I think the paper supports that well. So it's hard to say it's not Bayes too, because he comes up with the probability rule, and we don't know what Bayes knew or didn't know, but I've read a lot of historical overviews where people seem to suppose they know. And it's like, what's your evidence? And if you trace it back, it's like, I'm not convinced. I don't know what he knew.
There was a bit in the paper that kind of suggested that there was maybe parts of the Bayes' paper that wasn't from Bayes himself.
Yeah.
So there's a bit about that.
I think it's just like all history. So there's no way, like even my ideas that I think are totally unique, I got them from somewhere. Something came together, and did I cite exactly what I was thinking about, how I learned things? Sometimes we hide things. And it's like, I don't want you to know this is what I was thinking about when I came up with my genius idea, and then I'm really just lucky. So I think it's like any historical thing, and to attribute too much credit to one person is probably a mistake. I like to be contentious just like anybody else. It's a fun argument, just as long as it's fun, where we can argue back and forth. I like to support Laplace, and I like to tell the International Society of Bayesian Analysis to stop spending $1,000 cleaning Bayes' grave and go cleaning Laplace's every once in a while. That seems to rile people up. I'm just joking. So I don't care what they do.
I also think it's interesting to note, when I was reading through it, they were talking about how Laplace hadn't read Bayes' paper when he did a lot of his work.
Yeah.
And for a while that was something that caught me. It made me feel like it shouldn't be him. And then I realized it doesn't matter if you read Bayes' paper as long as you popularize the work.
It's hard to know. So did Jimmy Page really come up with Stairway to Heaven? So we kind of know the answer, probably not totally. So, but some of the parts are sweet. So that he did, and it's hard to know. So I think, yeah, absolutely. Laplace got his ideas from somewhere. Did he read Bayes' paper? We don't know. Did Leibniz and Newton read each other's papers? Probably. So will they admit to it and they get into a big fight? Personally, I don't get it. It's a good thing these guys aren't fully overlapping, so they didn't have to argue about it. Yeah, it's an interesting thing. David, do you have a comment you want to make about it?
One thing I noticed about the paper was, a lot of the debates about the meaning of probability
Yeah.
seemed to kick off after Laplace.
Yeah.
Like they were arguing about
Big time.
whether it was like subjective or objective, and that seemed like
Yeah.
probably it was Laplace's work that got people to realize what was going on when we were doing Bayes,
Right.
and thinking like, I think he made it more clear that the prior was a choice, and that like the role of choice in doing an analysis of a Bayesian sort, even though the concept of analysis was still developing at that time. But I also think at that time, people were trying to remove themselves from the process as much as possible. That was the popular thing to do. They wanted to be objective.
Yeah. It's interesting. These are long-winded debates. I like what Dave Finetti said about probability. He says probability does not exist. And what he's really alluding to, at least this is what I think he's saying when he says this, because it's just a blurb in one of his texts. So it's in the preface and it says it in bold. So probability theory, volume 1. I can bring that in and we can look at it together. I think what he's saying is all probabilities are conditional probabilities. And what you choose to condition on probably makes more of a choice. Which covariates did you include in what? You know, shift your beliefs about things. So I think he's saying you have beliefs. There might not be an inherent probability distribution function out there generating all this stuff. And I kind of like that. A lot of people take this to mean you can use any prior you want. And I think that if that was truly what you believed up front, and we would have to even know what that meant. Cognition and how does it work? And that's a touchy subject. I won't even touch it. Somebody asks me what somebody's thinking. No, it's a lightning rod. So can I predict what they're going to do with it? That's a different question. So I like the philosophical nature of choice and belief and all of that, but it's not compelling to most people. So we're going to play around with that line and talk about these choices and what they actually result in. So I don't think anybody was saying you just come up with any probability function, you try to convince somebody else with it, but the nature of belief is subjective. And I think that there's truth to that. Saying that, can we come up with compelling arguments that we would all follow in good procedures that have good theory behind them? And maybe in some sense we could call that objective. So I'm not going to argue that it necessarily is objective. I'm just saying people like to call things like that objective. That's not this class. So I want to teach you how to do things. I still want to talk about this stuff every once in a while. So we'll go through and check this out. Mostly I just want to check your plots, see if you know how to compute an expectation. And if you do, and that's no problem, then cool, you're in the right place. If you can do an integral, and you can complete the squared and stuff like that, even better, because we're going to be doing that all the time. Okay. I think next up, let's jump to this, and then we'll go to the simulation study. And of course, we can discuss this more if you'd like it for your session. I think that's a can of worms in itself, and we could probably go on tangents for quite some time. How long did it take Steve Feinberg to write that paper? So he went on for a while. There's obviously an army that unfolds right around this period. Savage and Jack are doing Bayes. Jack was here. So that's the cool part of this. Is I.J. Good, when all this is happening, is no longer at Princeton, he's no longer at Cambridge, he's no longer at Bletchley Park, he's at Virginia Tech. And he spends 25 years of his career here in bulk, threatening to leave all the time, so that sort of thing. And then he ended up extending his, decided to come out of retirement to come back. He likes it so much. This is a theme of Blacksburg. Anybody that's ever been here knows they want to come back. So lucky us, we got to keep Jack. Second year I taught this class, Jack passed away, and I had seen him the night before. And I was like, trying to tell a story like this. It didn't go well. So, anyway, we'll pull out all the emotion. That was 16 years ago. Let's go to this example, where we're trying to construct, probably because I just need to get to that comma. So I was trying to think about it. It just doesn't flow if I do that. So I want to build this up. Again, we're saying xi is normally distributed with mean mu sigma squared. So that's just some notation. You can't do anything with that. So other than understand an idea, I'm saying the xi's are coming out of this normal distribution. It's got a mean, it's got a variance. So I usually just write the sigma in there because that's the distance to the inflection point. But that's just measuring how wide this thing is in some sense. Keep in mind the normal is a pretty constricted distribution, and it comes down at this exponential rate. It's actually quadratic in the deviation from mean, and that's being slammed down exponentially. You can't get away from that, and that's where a lot of people make some mistakes. And so we'll try to deal with that mistake throughout this class, but learning everything about this model is necessary to fix the mistake. And that's what I really like about Bayes, it's very modular. If there's something you don't like about your distribution, you can build up a hierarchical model and kind of fix those things step by step. And that's what a lot of this class is going to be about. Normal distribution, I've got this stuff, so I might say f of xi given mu sigma squared is equal to 1 over 2 pi square root sigma e to the minus 1/2 xi minus mu squared over sigma squared. So that's just the probability sampling density, which represents this curve. It doesn't move, and this xi is going to be selected out of this curve, where I'm going to select regions to pick that xi, and I'm going to pick that xi with probability proportional to the area under that curve. So you can start to squish that probability measure together, and then you get the actual instantaneous rate, which is the density function. So that's the sampling distribution right here, the sampling density, and if I want the likelihood, I can just do this. I'm going to do this right here. I'm going to say if I wanted the joint likelihood and kind of overextend the question, I can just do this. So I've got the x's, I've got the relationship, the parametric relationship between the xi's and the mu's, and I'm going to use that parametric relationship to help tell me and guide me as to what these two parameters are given the data. So why would I do that? If this relationship is responsible for developing the xi's and telling us all about how those xi's are distributed, it's rather natural to think that exact same parametric relationship can be used in reverse. And that's the idea. We can develop principles on that in theory, but I think it's just kind of a good idea. A lot of people use that idea. So back in the day, likelihoods were contentious, and now every type of statistician I know uses likelihoods. So lots of things that people used to like to argue about. Some people are like, okay, it means different things to different people, but we all use it. So likelihood is proportional to I goes from 1 to n, all of these functions. So I just do that. That's because everything was IID. So meaning that the mu's and the sigmas weren't changing. I wasn't changing the distribution at every step. And what I had selected before didn't have any influence on what I select next time. Everything was determined by mu and sigma squared in the distribution. So it's underlying parameters and they don't change. So I can product this up, and then I can use this parametric form to help guide me into where the mu's and the sigma squareds. So this is just going to look like this. I'll skip a step. Sigma, I'm going to power that up. N times, that's constant. The only index in here is the xi's. So it's not in the normalizing constant. I like to think of it as an integrating factor because as a function of sigma, this is hardly constant. So careful with the language. E to the minus 1/2. Sum I goes from 1 to n, xi's minus mu squared over sigma squared. So same thing, and I can expand that out. So let me just rewrite this. Keep the exact same thing. E to the minus 1/2. And I'll do this in 2 steps. Eventually I'll be doing this in just 1 step and writing down what the answer is. So this is going to be the xi squared minus 2xi mu plus mu squared divided by sigma squared. Carry that over. And let's just do 1 more step and look at the terms. Sigma to the n, e to the minus 1/2. I'm just going to write this up into 3 different terms in here that we can look at. So this is going to be sum of the xi's squared. So I'll keep the indices in there. Divided by sigma squared. This is minus 2. Give myself a little bit of room. Minus 2. I'm going to say sum of the xi's mu over sigma squared. And then I'll say plus n mu squared. So instead of using the summation operator, I'm just going to sum that constant up right away. N times, it doesn't change, so it's just multiplication. So keep in mind, there's a minus 2 term here. We're going to be looking at this a lot in the next several days. There's a quadratic term. What is this a function of? This is a function of these 2 parameters right here. And so where do the mu's show up in here? It shows up quadratically there, and it shows up next to this minus 2 linear term. So this is linear in the mu's right here. So that's just a prelude of something that you're going to be memorizing and just remembering over and over again. So that's what normal distributions look like. I can write them like this, I can write them like that, they're all the same. So I want to point out, I can factorize this thing out right here. This has to do with sigma, it doesn't have any mu's in there. So I could end up getting rid of this, and I could rewrite this like this. E to the minus 1/2 sum of the xi squared over sigma squared. So I'm just going to rewrite it like that, and this is just being multiplied in there. So this factorizes out. And I will say, if you're doing inference on mu or sigma squared or both of them, if you use this form of the likelihood, written down here, written down like that, you will do no wrong except for on a computer. So keep in mind writing things down on a computer where you might have these rather large numbers that turn negative, that turn them e to the minus, turns it rather small, and you're producting that stuff up. That can be a bad idea to do it that way on a computer. And we'll see examples of that. So we'll challenge your numerical analysis and give you some solutions to that. Same thing on the chalkboard though. Doesn't matter how I write it. Same equation. I want to write it down a little bit differently. I had said last time if I were doing inference on just mu, what that means is this joint equation in terms of mu and sigma squared, if I were going to treat this as just a function over mu, it means that sigma squared is a constant. So that would be a constant right there, that would be a constant right there, that would be a constant here. If you don't like that I wrote sigma here and you want it to be sigma squared, just make sure you tuck it inside that standard deviation sign, or that square root sign. So if I were thinking about this in terms of a conditional equation, it's the exact same equation, except I have constants sitting here. Now all of a sudden this term that I factorized out is constant in terms of this. So if I wanted to get rid of something and make this a little bit simpler because likelihoods are really proportional, and I've written equal up here, but I really don't need it because it's all proportional to the thing that I'm trying to solve for. So it's just up to proportionality I define it. I can get rid of this, and I can get rid of this. But I'm still going to have those terms right here. They're the functions of mu. I can't get rid of those. So there's a linear term up here and a quadratic term that define this likelihood function. If you wanted to write all this stuff down, it's just like multiplying your likelihood by a constant, because sigma squared never changes. I could rewrite this a little bit differently. I could have done this, and I did this last time. I wrote it down this way. Sigma over root n, I've got my square root sign there, e to the minus 1/2 x bar minus mu squared over sigma squared over n. So I had made a claim that this, when I end up bringing this over here, and I thought of it as a constant, that this thing right here is proportional to that. So let's just show that. So 2 pi sigma over root n e to the minus 1/2 x bar squared. I'll write this up into my 3 terms. This is going to be sigma squared over n minus 2 x bar times mu over sigma squared over n plus mu squared over sigma squared over n. So I can do the same thing here. This is a constant, and I can factorize it out. So I can stop thinking about this. That's a constant. This is just some other constant. They don't match. So those parts don't match. So the joint distribution needs you to treat sigma differently than doing it this way. So the only things that don't match in these 2 forms are the treatment of sigma squared, not the actual mu. So I still have this, the minus 2 term. We can look at this. Keep in mind I can bring that n right up here and say this is x bar times n. Same thing happens right here. This sum of the xi's right here is just x bar times n. So what is x bar? Sum of the xi's divided by n or multiplied by n. It's another name for sum of the xi's. So these terms match right here. They're exactly the same. Same with that one. This n also gets brought up. It's this n right here. So as a function of mu, these are the same equations. As a function of mu and sigma squared, they're different equations. So that's because we only define this up to proportionality. And so some of you that have taken a more advanced statistics class like grad school Inference will notice what this all means. And you would say, oh, the only part that mu depends on in terms of the data, keep in mind that doesn't have a mu in there and it can be factorized out. If I couldn't factorize this out, I'd need to know what x bar is. But you don't need to know what x bar is necessarily. Sorry, let me say that again. I don't need to know what some of the xi squareds are in this equation. Just need to know what x bar is. So, and this part just deals with the asymptotics of everything. So that shows up. If I wanted to know sigma squared, I need to be able to compute that part of the data. Some of the xi squareds. When I use this form, that's not here. X bar squared is not some of the xi squareds. If I gave you x bar squared, you cannot give me the sum of the xi squareds. If I give you some of the xi squareds, you can't give me x bar squared. So those are different bits of information. So what somebody that's taken a very advanced statistics class would tell me, if I want to know what sigma squared and mu are, I need to tell you what x bar is, and I need to tell you what some of the xi squareds are. That's the sufficient statistics. Those are the minimal sets. If you want to know more about that, that's the spring class. And you can learn all about that theory. We're not teaching that here, but we'll allude to it. So for this equation right here, if I want to know mu, all I need to know is x bar. So x bar is the sufficient statistic for learning mu. Please.
Sir, the first term in that expression, I think the first term of the exponential, I think the x bar square is different from the x square bar.
That's right.
So I think it could be an anomaly, I think.
So I'm just saying these two terms are different from each other. You'll never make them the same. And so once I've written this down, if I wanted to know what sigma squared is, I made a huge mistake. I don't have the information for sigma squared in here. All I've created is the information for mu in this form of it. This would be a lot faster to work with this form if you're on a test. And that's my point. If you want to work with that form, that's fine. If you use this form and you want to learn what sigma squared is, so if you use this form and want to learn what sigma squared is, you will have made a big mistake. You need to use a form that is proportional to this form. If I wanted to know what sigma squared is, period, and not mu, and I use this form, I will have made a big mistake because this doesn't have the information about sigma squared. This one still does. So this has the information about all of them. So the joint likelihood. And so how do I get the conditional likelihoods out of the joint? I just pin down the parameters. If I've already simplified it into something like this, how do I go back? You can't. You have to form the full joint. So hopefully that'll just keep you out of trouble. And know that once we do variance analysis, if you use this form of likelihood, you're about to make a mistake. And the mistake is in two places. It's here, and it's also in here. That gets powered up n times, and there's only one of them here. So that's also part of the asymptotics. So if you're ever doing variance on the inference, make sure you're using more information than just x bar.
I guess one thing I'm confused about is like in the left version where we're like using this different form, what was the, it seems like the whole point of it was to like make it a more condensed notation so you don't forget all the other stuff.
That's it.
So what was the point of writing the coefficient that depends on sigma?
This one. Just to show it to you.
Or yeah, I guess.
Or this one.
Well, I was talking about the one above it, but it's the same one.
Yeah, it's the same thing, just to show you.
Okay.
So just to make you think about two different things and why it's important. Why would I use this one right here? Taking a log over this and coding it up on a computer is really easy. I don't have to take a sum, and I can use just this equation.
And what do you say x bar is? What is x bar?
X bar is some of the xi's divided by that.
Okay, but it's not the same from the x bar. It's not the same x i's as shown in this equation. Because you were saying
These ones are xi squareds. They're all the same xi's.
okay.
Equivalent xi's, but this term is different right here. And from this term, if you just had x bar, you could never unravel that, what that is. You need all the xi's to tell me what this is.
Okay. I think that makes sense. Okay, thank you.
What that means is some of the xi squareds is sufficient for sigma squared, accompanied by x bar, because I can't factor out this one from that either, so I need both of them together. And that kind of makes sense because our usual estimator that they would teach you in a Stat 101 class is this thing. We'll talk about the n-1 later. They teach you that, so you need the sum of the xi squareds and x bar all together. So anyway, what I want to use for just a second is just this one. So this is just a warning shot that if we're doing inference on variance, which we're not doing this very second, this would not be the right likelihood equation. This has been a point that's confused students for many years, and they usually have to make a mistake before they learn that lesson, including me. So I did this in grad school on a problem, and I remember missing those couple points and going, oops, it's trying to go fast. And that's why my answer is wrong. So again, if we ended up trying to build the posterior distribution for this, I can say this is proportional to my likelihood function for mu x sigma squared times my prior. So again, we're taking the engineering vantage point. They're just two functions I'm multiplying together. So I can write this down as e to the minus 1/2 x bar minus mu squared over sigma squared over n. I need that n in there, scaling everything, times maybe 1. And we're going to talk about this next time. If you think this is a funny idea and you're reluctant to accept that as a probability distribution, I'm with you. And I'll tell you what people mean later on and why they're doing it. I'll give you a couple different vantage points, theory and engineering. So that's next time, Chris. So I can write it down like this, and this is just super simple. So I look at this, okay, that's my posterior distribution. I multiply the prior times the likelihood. I like my random variables on the left. It's still the same function. So it didn't change anything. So I know where this is centered. This is centered at x bar, and this has variance sigma squared over n. So I could normalize this if I wanted to, because I just happen to know what the normalizing constants are. If you happen to tell me what the variance is, I know that I plug that in just right here, and I take a square root over the top. So that's where the variance goes. And the variance is right there. That's why that thing is getting factorized out, is sigma over n. The variance of x bar has the same mean as the original data, but the variance is reduced by factor of n dividing by n. So this is a real easy way to think about things. So this is just a Bayesian distribution. The posterior, it's the probability distribution of mu. It's where I believe mu lives. And it looks like this. Centered at x bar, sigma squared. I'll put the sigma over root n to be a little bit more consistent. So it looks like that. And so classicists, when they build a distribution, they build the distribution like this, centered at mu, and they're talking about the distribution of x bar. So they're going to say this equation right here is 1 over 2, square root 2 pi sigma over root n, e to the minus 1/2 x bar, centered at mu, squared over sigma squared. So they're thinking about the distribution of x bar. So that would be some x bar over here, and they might be computing p-values with this, and thresholding this, and seeing how far into the tail you are. And there's a complete symmetry with the way the Bayesian thinks about it if they use this prior. And they're thinking about things centered at x bar, and they're looking how far into the tail you go with mu. And it turns out if you say that a deviation between mu and x bar is extreme in one sense, you'll say it's extreme in the other sense too. There's a complete matching between the way the Bayesian at least computes the numbers and the way the classicist does. So if you've ever taken a Stat 101 class and I asked you to compute the probability that x bar lives in this tail, and I asked you if you were in a Bayesian class, what's the probability that mu lives in this tail right here? Keep in mind they're centered at different places. You'll give me the exact same number. So we'll see that when we confront hypothesis testing. There's sometimes agreement and sometimes agreement. What I just want to kick you off with is what does normal distribution look like and how do you calculate it? Let's switch back to the binomial problem.
For the form for the normal distribution, is that something we should be memorizing, or will that be?
You need it in your mind now. So make sure that's committed to memory by Friday. So it's going to be on your first homework. We're going to do a review session on Thursday. I want to make sure you know this stuff so early. You're going to have to deal with this in high dimensional form, and you're going to have to be fast. It's going to come up on a midterm. So that's kind of like memorization. So saying that, don't just make it a hard task of memorizing. Put it around you and work a few problems. And so just seeing it over and over again naturally will commit it to memory. Chris?
So for the n with the variance of the x bar seems sort of around. I get you get the n from when you expand that you needed to write it in that form, but we ignored the normalizing constant. I'm thinking out loud. I'm not totally sure I'm going with this, but I'm wondering if we hadn't ignored that, would we have still wound up with an n over there?
And then where? On this one?
Yeah, exactly.
This thing? You want to get the n here. No, it'll never happen. It'll never be there. So what that's telling you is that this function in terms of sigma or sigma squared is inherently different than that function. So you'll never be able to reconcile that error if you make it. If you're dealing with mu and just doing inference on mu, I don't care which equation you use. If you're doing inference on the variance and use this equation, you've made a mistake. So if you're doing inference on variance and you use this equation, no mistake. If you're doing inference on mu using this equation, no mistake. If you're doing joint inference and you use this equation, no mistake.
But with this second equation, if we got rid of that, it would be just as valid, right?
Yeah, that's true. If you're doing inference on only mu.
Okay.
A few things to distinguish there. Okay, let's go back to here. We'll kick it off next time because we've spent a little bit more time talking about this, but at least we don't have to talk about it after the midterm one. Try to avoid that mistake. Here's where we were last time. We simulated some data and we developed a posterior distribution. Keep in mind this is a binomial example, so I'm flipping a coin with probability p. I'm building a posterior distribution. The alpha and the beta are the hyperparameters in my prior distribution. So in my analysis, and I wrote down the solution to this analysis as we were kicking off class, the solution is this. Beta has these parameters. And minus some of the xi's plus beta. So when I write this down and this is the posterior, you can tell, oh, I know which prior he used. There's only one prior I could have used to develop this, and that's the beta prior. So I should probably be polite and tell you all these components right here. This was a beta with these parameters. Parameters that underline your prior distribution are called hyperparameters. Write that down. And it's one of the only naming conventions that we got right in statistics. They use it all over the place too, but it's a good word. So, and you know what the likelihood function looked like. The likelihood was just this. Proportional to p to the sum of the xi's, 1 minus p, and minus sum of the xi's. So these two ingredients result in this thing right here, the posterior, and that's what Bayesians do. They do inference off the posterior. Apologies. Let's just resimulate this, just to remind us how this works. It's just some code. We'll slow this down a little bit later, but we can at least do some sensitivity analysis and see what happens. So this is my posterior. My truth is 0.4, so the probability of the coin that I'm flipping is the blue line. My posterior forms by doing that. and I used a uniform prior. So that's a proper prior distribution. We've used Bayes' theorem like it's been taught to us in step 101 classes, and this is the resulting function. And again, I want you to just see how flexible this is as we start flipping this thing. There was a lot of asymmetry early, and it ended up tightening up and becoming symmetric. So, and every time I do this, I'm generating new data. So it's new data every single time. And every time I do this simulation, it seems like this posterior distribution is encapsulating the truth. So it's consuming it. Let's go again. It's not exactly in the middle. If the answer was exactly in the middle every single time, there'd be something wrong. So this posterior distribution is describing the probability of where it believes the blue thing is. The data coming out of it is random, so there's some inherent uncertainty there. I could end up changing the prior distribution, and I could twist it around. So I've got my uniform prior by working through a beta. A beta 1 is a uniform. So I could change this, and I could end up saying these are other numbers. So I could make that like a 10 or something like that. That's my alpha parameter. So I'm stacking the successes, and I'm believing the weight between my coin a priori is maybe 10 to 1. So I think that maybe this coin is heavily biased by a factor of 10 over to the right. So that's what this prior distribution looks like. So I've got all these prior weights. I didn't put very much weight over on the left-hand side, and the actual truth was over on the left-hand side. So it's no surprise that my posterior gets yanked over towards my prior beliefs. The dotted red line that you can now see that's been revealed is the likelihood function. And so I would say for any Bayesian analysis, we probably want to look at pictures like this. Where's your prior? Where's your likelihood? Where's your posterior? So if I saw something like this, I'd go, okay, I guess that's an okay answer. It's over in the tail. I think I pulled this thing over, but maybe that's not a great problem. So that wouldn't be very compelling to use for somebody. I don't know how I can defend that. So maybe half the time I use a prior like that, and maybe half the time I use a prior like this. So on average, I'm using a good prior. I don't think that would be a very compelling statistical argument as well, but the same thing happens over on the left-hand side. So, and it's pulled everything over to the left. And so again, it would be hard to justify this prior unless you happen to believe I use coins that have this probability distribution for the probability of landing heads or tails. So again, hard to compel somebody to do, but there's other priors that you can use.
So if we use like a bad prior and because it seems like as we flip the coin more times, as we add more data, it gets closer to a quote-unquote better posterior. Is there a way to like quantify how that
Totally.
works?
Yeah, absolutely. And we're going to look at that later. And so try to quantify how much contribution of our inference is coming from the data and how much is coming from the prior. And I think in this analysis it's rather easy to do, and we'll look at that next time a little bit more closely. So you might be thinking, well, maybe I want to be objective in some sense, and I want to make this coin fair. Using a 1 here and a 1 here seem to work pretty well. But maybe I want to a priori think that the coin is 0.5. Now, some people will say that's objective in itself, but I just think it sounds like you're a coward to me, is what it sounds like, 50-50. So how certain are you of that? Not very, but I don't know. So I do think principles like that, they do sound good, and maybe there's something good in there, but this prior that I picked stacked a lot of weight around 0.5. And how you stack weight in an unbiased way is probably what I would think about whether or not you're being objective in some sense. I wouldn't think that this is objective. You very much think that the coin is around 0.5. And maybe you've got a lot of experience to justify that. So you could say, no, I'm going to use the data to show me the deviation from 0.5 because I expect 0.5. And so this is helping me to understand what the superposition between those two ideas are. Last question.
Is there a factual difference in using like 1, 1 or 10 alpha and beta?
Yeah, I think so. As we can see, the posterior is becoming better and better as n goes higher. And so it depends on how big n is. So So if you just had a little bit of data, overcoming that strong prior belief or that diffuse prior belief would mean different things. If n was infinity, we get all converge to the truth. That's true for classicists, frequentists, whoever you are. If n was actually infinity, we wouldn't need to do statistics. So that's just a concept. So it does matter, but it's more of a question of how big is it. One more question?
I mean, is this online right now?
This is online code. So you can
I
download
looked on the
online.
website and I couldn't find it, so I just.
I think it's on the webpage. Is there a .m file there? I think it's called the Binomial Simulation.
I saw a web page like I saw an file like it was a different file.
So really?
Yeah, so I can check again.
Okay. If it's not the right file, I'll update it. Thanks, y'all. We'll come back and play with this more next time. And I'll tell you about the beta half prior, which is probably the prior I would default to. But more to the point, would it make a difference? It depends on how close the key is to the boundaries of the space. Thanks, you guys. Just a reminder, we'll do a review on Thursday. We'll do a review on the Thursday after as well. We'll look at doing about 2 weeks.
Yeah, he uses his web.
So it's absolutely decent where you know things. Where you expect things to be. There's all kinds of good things. It's just saying that to somebody in general. It's like, these things are different things. Knowing that, if you do that, I think my responsibility. Yeah.
对啊，是这样，但是他对，是的，所以我不是学统计的，所以有的东西我有他这项是在做，但是他把这项因为你用过的非常多。